Alright, so what I'm going to do is I'm going to do a breakdown of, we started the last time in class of the different bonding forces that hold things together, and what I'm going to do is I'm going to break down two of the categories so you can tell them apart when you're looking at them and be able to rank the forces, because that's one of the key things in AP. So if you look here, we have covalent bonds, right? So here's our chart of there are four different types of bonds that everything's made of. Covalent bonds, which means when we say IMF, that's what we're referring to. Covalent bonds have to have all nonmetals. So if you look at something and it's all nonmetals, you know it's covalently bonded, which means it has IMF. There are ionic bonds, which are a metal plus a nonmetal. You all know how to spot that from the periodic table. So they're held together with ions, and that's the major bonding force. Metallic bonding is when you just have a single metal like aluminum, platinum. The easy way to spot that is just having a single metal. Then finally, network covalent bonds, which are by far the strongest. Diamonds, SiO2, silicone. There's only a couple you need to know for the AP exam, and those are just memorizing them, and you recognize them as soon as you see them, kind of like the 6 strong acids. So then when we get into covalent bonding, we know that they're ranked. There's 3 forces. The first one is hydrogen bonding, is by far the strongest. We use the fun rule, which means that fluorine, oxygen, or nitrogen directly bonded to hydrogen produces hydrogen bonding. Second strongest force is dipole-dipole. Third strongest force is London forces. You can actually tell the difference between London forces and rank them, and that's what they ask you to do on the AP exam, and it does come up, especially in the essay section. How do you tell the difference in London forces? The first thing is number of electrons. The more electrons a molecule has, the more the electrons can get caught or be polarized. It's more polarizable. So the first thing you do is you tell if it has more electrons, it has greater London forces. How do we normally tell electrons? We can basically infer it from its molar mass, and I'll show you on the next coming up slides. You'll see that. The other thing is elongation. The longer a molecule is, the easier it is to get distorted. So if you're comparing two molecules and one's more elongated than the other, and I'll show you this coming up, then you know that it has greater London forces, because you're going to be asked to rank these, and so those are the 2 criteria for London forces. Ionic bonds. When you go to do ionic bonds, metal and a nonmetal, how do you tell the difference? Well, bigger charges, stronger bonds. I'll show you the law. If they have larger charges than the ions, automatically it's going to be stronger. If the charges are the same, what's the second criteria? The second criteria is the smaller the ion, the closer they are, like little magnets. So the closer you bring them, the stronger the bond, and I'll show you that as well. So this is really what we're focusing on today. We're focusing on basically differences in IMF or differences in ionic bonding, and really understanding the criteria and being able to apply it like you have to be able to do on the AP exam. These for right now, I'll show you this later next week. This one we don't really have any criteria for. All right. So, first and foremost, we know that hydrogen bonding is a special case of dipole-dipole forces. You have the fun rule, and the forces are abnormally high. They're very, very strong. It requires an H directly bonded to an electronegative element, F, O, or N, so you have to basically look at it. If you go here, I see a hydrogen bond right there. H and an O, between the 2 molecules, it'll create hydrogen bonding. An N to an H bond, fun again. So you have hydrogen bonding occurring. Here you have the strong, very strong dipole. So if you look at all these molecules, you see the HF, you see the HN, NH, HF, HO, HN. So looking at its structure, its Lewis structure, looking at its structural formula, you can see it. So that's the first thing you have to be able to tell and be aware of. If we look here, which of the following substances exhibits hydrogen bonding? For those that do, draw the molecules with the H bonds between them. Right here, there's no fun in this molecule. It lacks fluorine, oxygen, or nitrogen, therefore it cannot have any hydrogen bonding. If you look right here, I zoom in, I see the O and the H, which means structurally those 2 are bonded together. What is this going to look like? It's going to have a C with 3 H's. Then it's going to be bonded to an O, which is bonded to an H. And when you're done, that's what the Lewis structure looks like. This is going to create hydrogen bonding, which is going to have stronger intermolecular forces. which will be a higher boiling point, higher melting point, higher freezing point. Same thing here. You notice this when I go to draw this, CH3, single bond to a C, which is double bonded to an O, which is single bonded to a nitrogen, which has two hydrogens trailing off it. So right there, I have fun right there. H directly bonded to a nitrogen means that this will also hydrogen bond. So B and C exhibit hydrogen bonding based on its formulas. Next type of force, dipole-dipole. Polar molecules, the more polar it is, the greater the attraction is going to be between them, but you're not asked on the exam to determine differences in polarity. Just know that polar molecules have strong intermolecular forces, not as strong as hydrogen bonding, but strong. So you have one side of the molecule will be negative, the other side will be positive, and you get dipole-dipole interactions. What effect does this have on the boiling point? Well, as you see the red area represents polarity. As a molecule generally gets more and more polar, what happens is you'll see its boiling point start to increase. So the more polar a molecule, the greater its boiling point, because the molecules become more sticky, they're harder to separate. All right? Next one. London dispersion forces. This is the one where you have to actually apply the most criteria. It is, first of all, the weakest of all the intermolecular forces. It's the bottom of the list. It is possible for two adjacent molecules to affect each other. Really what happens is in an instant the electron clouds become distorted, and that's what we call an instant dipole or an instantaneous dipole. A momentary polarity is caused. An instantaneous dipole, it's polarizable, the molecules attract to each other. Here's a typical, I showed you this before, typical helium atom. Notice the electrons are dispersed in the atom evenly. What happens for a split second is one gets caught on one side and it becomes distorted. The cloud becomes distorted. One side becomes negative, one side slightly becomes positive, and so you have a negative and a positive, and you actually have helium atoms, which are nonpolar. It's a noble gas, which are always nonpolar, but what happens is for a split second, they have London forces. One side becomes negative, one side becomes positive, and they are attracted to each other briefly, but that is why it's the weakest. Here's the key. This is really important. Polarizability. The definition of polarizability is the ease at which an electron distribution of an atom or a molecule can become distorted. There are two things that increase polarizability or cause polarizability to increase. First one is the greater number of electrons. More electrons, more distortion. So if you look here, these compounds, the difference between these compounds is as you go down, the number of electrons are increasing. How do we tell? An easy way to tell, the reasoning is, or the way you can tell is, as molar mass increases, so does the number of electrons. So we can infer, it's the reason why London forces increase is not because of the molar mass, but is because of the greater number of electrons, but we can use molar mass to infer the greater number of electrons. So as you go down this way, the number of electrons increase. What do you notice happens to the melting point? It gets higher and higher and higher. The reasoning is because the greater number of electrons making the cloud more polarizable, therefore it exhibits greater intermolecular forces. The other polar part of polarizability is the more diffuse the electron cloud, meaning the more elongated the molecule is, the easier it is for the molecule to become distorted, or the electron cloud to become distorted. Alright, so back to full screen. Here we go. Alright, so if you look right here, here's a perfect example. Molar mass and boiling point. Remember the relationship? As molar mass increases, the number of electrons increases, and that's the key thing you need to know is number of electrons. So as you go from helium, which has a boiling point in Kelvin of 422, neon, its mass increases to 20, boiling point is 27, 39.95, 87. Krypton is 83.80, 120. So as the increasing amount of dispersion forces or London forces kicks in, you have a greater boiling point. Same thing with the halogens. As they increase in their mass, you notice the boiling point increases, because these are both nonpolar molecules or atoms. The noble gases are nonpolar atoms. The halogens are nonpolar molecules, and basically what happens is, since they only have London forces, that's the difference between them. It's greater number of electrons. Another idea is shape and boiling point. Pentane and neopentane, they're isomers, which means they have the exact same molar mass. But yet, if you notice, there's differences in boiling point. Why? Well, they're both just made of carbon and hydrogen, which means they're always going to be nonpolar. So the only force they have between them is London. So London and London. The difference is these have more points for dispersion forces to act because the molecule is more elongated. The more elongated a molecule is, the greater the London forces. Whereas this is more like a little ball. You notice the difference in boiling point. Higher boiling point means higher intermolecular forces. We already knew that anyway based on the elongation. Greater number of London forces because of greater amount of elongation. All right, next column over is ionic compound in your sheet. Ionic compound is a metal and a nonmetal. If you look at Coulomb's law, states that attractive force is proportional to, and you don't need to be able to calculate this, the magnitude of the positive charge and negative charge that goes on the top. So really what you can do is multiply the charges from the two ions and get a value for that, and that'll kind of give you an idea, a way to ballpark the difference in the charge. Two things, and if you notice, radius is on the bottom. First thing is, bigger charges mean stronger bonds. The bigger the charge overall, the stronger the bond. Smaller the charges mean weaker bonds. Charges close together mean stronger bonds. So the radius kicks in because the closer you bring magnets, the more attractive the forces are. Same thing works with ionic compounds because they're like little magnets. This is all based on the idea that ionic compounds form lattices. This is a lattice structure. Basically, the ions form lattices and they're attracted to each other. So if you're comparing like lithium chloride to magnesium chloride, right? Which one has a higher melting point? Because we talk about with ionic compounds, we talk about melting points. Well, the answer is MgCl2. Why? Because Mg's charge is 2 plus, Cl charge is negative 1. When you multiply the whole thing together, if you take the absolute value, the overall charge on the top is going to be 2 of the equation. This one, lithium, has a charge of plus 1. Chlorine has a charge of minus 1. You multiply the values, the charge values, you're going to get 1 on the top of Coulomb's law. You're not going to have to take and do all the math on the AP exam, but you're inferring based on the charge what kind of forces are the strength of the forces holding them together. So automatically you would say MgCl2 has a greater melting point because the charges on the ions are larger. Larger charges on the ion, higher forces holding it together, ionic forces holding it together, means that it's a higher melting point. All right, here we go. What types of intermolecular forces exist between each of the following molecules? If I draw this out, you get HBr, ... First of all, there is no hydrogen bonding, but there is dipole. So this thing exhibits dipole forces. The other thing is anything that's made of nonmetals always has London forces as well. So for HBr, I would actually list dipole, the strongest force. But on the AP exam, if I wanted to be thorough, I would also say that it also has London forces because it's covalent. Covalent compound, all of them have London forces. Strongest force in this molecule is dipole. If you look right here, CH4. If I go to draw it out, draw out CH4. If you look right here, there is no hydrogen bonding. That molecule is not polar based on what we learned in the last chapter. So the only forces in that is London. Last but not least, SO2. When you go to draw SO2, this is what you end up with. This molecule is definitely polar. It has no hydrogen bonding, but it does have dipole. But remember what I just said previously, anything that is a covalent compound will also have London forces. So if you're doing it to practice for the AP exam, you'd want to make sure you list that. All right. Key thing to remember is when you're going through intermolecular force questions, they're asking you to critically think. And all you're really doing is just remembering this. Intermolecular forces are bonding forces holding something together. The key thing is how sticky they are, like the example I did in class with the cups. The stickier the molecules, the greater the IMF. And what does that really mean? This is key. It means that your boiling point will be higher, direct correlation. Your melting and freezing point, which is the same temperature, will be higher. And then vapor pressure, which we'll get into a little bit more next week, is lower. It's not a direct relationship, it's actually inverse. Because the higher vapor pressure comes from the less sticky the molecules are. So if you look here, we go to the next one. Here's an example of what you have to do for the homework. They're going to ask you to do this typically a lot. So the way it works is you do this. You take two compounds and you have to figure out the difference in, so for example, I have MgCl2 and PCl3. First thing is I have to identify the dominant force in each substance. So if I look here, MgCl2 is a metal and a nonmetal. It is going to be ionic. PCl3 is going to be covalent. Its dominant force is going to be IMF. Now, first and foremost, ionic compounds are always stronger than IMF in the ranking system, because if you look at that chart at the beginning, we always say IMF is the weakest, then ionic, then network covalent. We don't really talk about molecular too much in AP. It's in the mix, but we really focus on IMF is the weakest, ionic is the next strongest, and then network covalent. So automatically this will have a higher boiling point simply because it is ionic. Now, PCl3, what type of intermolecular force does it have? It's actually a dipole. When you draw it, there is a lone pair of electrons on the central atom. So that's how you would do it. You'd basically list the forces in each and then identify. I would check this having a higher boiling point. Okay. So let's do the next one. B. So if we look at B, if you look right here, that is a covalent molecule, that is a covalent molecule. So they both have IMF. What kinds of IMF forces? Well, this one, I see hydrogen bonding right there. The end of the H is part of the fun rule. This is going to have H bonding. Since it is IMF, it's also automatically going to have London as well. So write London there. This molecule looks like this. C, H, 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 the way it's written, with an F attached to the C. So there is no hydrogen bonding. Now it is a dipole because the terminal atoms are different. So I would say this molecule has dipole, and it also has London since it's covalent. Then the last thing is who has a greater boiling point. It would be this one. This molecule here has a greater boiling point because of the hydrogen bonding. Okay? Next one. When you look right here, C, you have two molecules. Well, the first thing I notice right away is I see hydrogen bonding right there, and I see hydrogen bonding right there. So, both of them exhibit hydrogen bonding. How do you tell the difference? What's the tiebreaker? Well, if you look at the molecules, the difference is going to be mass. If you have two molecules that both have hydrogen bonding, how do you tell the difference? Then it's going to go to London forces, whoever has the greatest London forces. That's how you break the tie. This has H bonding. It's supposed to say H bonding. This has H bonding. And then you look at molar mass. The molar mass of this is how we infer the number of electrons. Automatically, I know that this is going to have a greater mass because that has that extra CH2 in there versus the first one. So automatically, I know that this will have a higher boiling point because I'm going to say or infer it has more electrons based on a higher molar mass. So because this has more electrons, we say it has a higher boiling point because it has greater London forces. Last one. If you look right here, D. You look at the last one. If you notice, the masses of these are pretty much the same. They're pretty close, actually. This is dimethylbutane, and if you calculate the molar mass, these are pretty even. You notice there's only carbon and hydrogen, so they both have just London. So how do we figure out between two molecules that have just London forces, who has a greater amount of London forces? If the masses are close to being the same, the thing is elongation. So the first thing is you look for greater number of electrons. If the electrons are about the same or the masses are about the same, the next thing you do is you look for elongation. In this case, this molecule is much longer or much more elongated, which means it's more polarizable. So in your justification, you would pick hexane has a higher boiling point, and what you would say would be it is more polarizable because it is more elongated. So it has greater London forces because it is more elongated. All right? Enjoy the rest of your vacation. I'll see you on Monday.